Okay, so now let's look at improper integrals. And before I jump into defining improper integrals and doing the sort of normal calculus teacher way to evaluate improper integrals, let's jump into a little example. So this is going to be an example of an improper integral. And we have the integral from 1 to infinity of 1 over x squared dx. And right when you see this, you can think, okay, geometrically, this is a region that's infinitely wide. It's starting from 1 and ending at infinity, and this will always be positive. So you might think, okay, if it's infinitely wide and has positive heights everywhere, won't this just end up equaling infinity? So that's actually not the case. Let's look and see what happens. So in here, I had a little graph, and I have a slider to make the integral go further and further out. This green function is 1 over x squared. And if I do the integral from 1 to 2, I get this area of 0.5. But as I go further and further right, you can see, okay, it's getting larger and larger because I'm adding more and more area. And eventually, as I go further and further right, you see it settles down, and eventually the area is 1. It's bounded, so it approaches this value 1. And that actually tells me that this integral will equal 1. Now you might ask yourself, okay, how did I have an infinitely wide integral whose value is 1? How did I get a finite area out of an infinitely wide integral? And if we look at this, here's the important thing. As I go further and further right on this function, okay, the value of the function is approaching 0. And so as I go further and further right, the height gets shorter and shorter and shorter. It still is a positive height no matter how far right I go, but it gets shorter and shorter and shorter, and actually gets shorter fast enough so that as I get this integral further and further right, it approaches 1. Now you can see this in the next example I have, where, let me get rid of these graphs. If I consider 1 over x instead of 1 over x squared, you see it's still approaching 0, but it's approaching 0 much more slowly. And as I do this integral and get a larger and larger upper limit, you see, okay, it's growing, but it doesn't seem to stop. As I go further right, it gets higher and higher and higher. So unlike the first example, this is not bounded. It does not approach a value. And we'll talk about this more later. So the important thing is that the green curve, it approaches 0 quickly enough so that the area as I go further and further right doesn't explode out to infinity. The red curve does not approach 0 fast enough. So now let's get a little bit more formal, and we'll see how to do this one analytically without looking at a graph as well. So improper integrals, I'll define those simply as integrals involving infinity. Now it can involve infinity in a few different ways, and we're going to consider what happens here. I'm going to write a bunch of notation. It's how you should rigorously consider these integrals. But there's a nice little shortcut, and I'll show you that in the next example. So one way to have an improper integral is if I have the integral from some number, some constant, to infinity of f of x dx. Or an integral from negative infinity to some constant of f of x dx. Or the integral from negative infinity to positive infinity of f of x dx. The correct, rigorous mathematical way to deal with this, because I can't actually put infinity into a function. If infinity is not a real number, it's greater than any real number. So saying what is infinity squared or what is 1 over infinity doesn't make sense. But what I can do is like what I did in that graph. I can consider the limit as the upper limit approaches infinity of this integral of f of x dx. Or for this one, I can consider the limit as the lower limit approaches negative infinity of the integral of f of x dx. And for this one, here's a little trick, and I'll show an example and I'll try to make it really clear for this. Since I have two infinities here, I actually have to consider it going two ways. So I will consider the integral from negative infinity to some value. I'll just say 0. It doesn't actually matter what we choose here. Some might make it a little bit easier in certain problems. But I'll go from negative infinity to 0 of f of x dx plus the integral from 0 to infinity of f of x dx. I actually need to consider both separately, and if either one of these goes badly, then the entire thing goes badly. Now, these integrals will have to be done the same way I did this stuff. I'm going to actually have the limits in here. So it's not just doing an integral, but we'll be able to take a little shortcut and consider it this way. That's if the limits are infinity. We also could have the function approach infinity. So let's just say that f of x goes to some type of infinity, or both, at x equals a. I would say x equals c. That'll be better for me, I think. If I have the integral from a to c, a being less than c, of f of x dx, that's going to be the same thing as the limit as as b approaches c of the integral from a to b of f of x dx. And I'm going to want to approach b from the left-hand side, because if a is less than c, this interval goes from a all the way up to c, but I don't need to go beyond c. Similarly, if I have the integral from c up to b of f of x dx, where f of x goes kind of crazier at c, I can write this limit as a approaches c, and since this is the lower limit, I'll approach c from the right, of the integral from a to b of f of x dx. And finally, if I have this this integral, let's say, from a to b of f of x dx, and c is in the interval a to b, so c is somewhere between a and b, then I'm going to have to split up as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. I need to actually consider what happens to both sides as things go badly. So let's look at some examples. I will show the first example worked out with all these silly limits, but as long as you have the right thought process, you can actually sort of skirt along and get the right answer still without writing all of this stuff out for this specific problem. So before I do that, the idea, just some terminology, because we're going to see some things where this happens. If something converges, that means that that limit is equal to some real number L, where L is not an infinity, a real number. If it diverges, that means the limit is going to be some infinity. Diverges means that it either blows up to infinity, or if the limit does not exist. So if we had an integral like one I saw earlier, and we'll see it again, that goes towards infinity, we would just say that that integral diverges. Example 1, and this is the same one we saw before, we'll revisit it. I'm going to the integral from 1 to infinity. Now, 1 over x squared behaves nicely everywhere from 1 up to infinity. It's going to be a positive number getting smaller and smaller and smaller, but this infinity is a problem. I can't just take the antiderivative here and expect it to work. So I will rewrite this as the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. So instead of considering an infinite limit, I just have a value, a variable, that is approaching infinity. And I can do the same integral work we did before, second fundamental theorem. So this will be the limit as b approaches infinity of the antiderivative of 1 over x squared. So let's do some work. 1 over x squared dx is the antiderivative of x to the negative second dx. I add 1 to the exponent and divide by that value. So that's going to be x to the negative first divided by negative 1 plus c, which is going to be negative 1 over x plus c. So I can do that. This will be the limit of negative 1 over x evaluated from 1 to b. And now, as I consider this, I can put in b and I can put in 1, so I have the limit as b approaches infinity of negative 1 over b minus negative 1 over 1. As b is approaching infinity, this right here is approaching 0, because I'm dividing 1 by a larger and larger value, so this approaches 0. This is actually equal to a positive 1, and so 0 plus 1 is 1. And so algebraically, you see we got this answer. Now this was a lot of work with all the limits. I told you there's a nice shortcut we can take, and here's the shortcut, and I'll do this for the rest of the problems. I'm just going to consider this as if it were a regular old integral, but as I do the work, I'm going to keep in mind that I'm not actually putting in infinity, I'm putting in a value that's approaching infinity. So I actually just write it like this. I do the antiderivative of 1 over x squared and get negative 1 over x. And I'm going to write evaluated from 1 to infinity. I'm not actually putting in an infinity, I'm actually doing a number that's approaching infinity, but this will always work. So as I put in a number approaching infinity, this approaches 0. When I put in 1, I get negative 1, and so that's going to be 1. Again, not rigorous notation, but it will always give me the right answer. This can just take too long for me usually. Let's see a couple more examples. So here is this example that we considered a little bit of. I have the integral from 1 to infinity of 1 over alpha d alpha. Now it looks a lot like our first example, but I don't have an alpha squared. So I'm going to use my little shortcut. And I'm going to say, okay, I know that the antiderivative of 1 over alpha is natural log of alpha. I don't need the absolute value because this will only be positive. Evaluate from 1 to a number approaching infinity. I'm writing infinity, but I'm considering it as a number approaching infinity. Well, I know that natural log is this graph here. And as the input grows, so does the output to infinity. So this is going to approach infinity minus the natural log of 1 is 0. And what happens here is this actually approaches, the limit's going to approach infinity. So I will say that this integral converges. Sorry, not converges, that's the exact wrong thing. Diverges. I was thinking about going back a second. So this diverges, and I'll leave it at that. The area approaches infinity will say that the improper integral diverges. Now, this did equal 1. Since it equaled 1, I could say that this integral converges. So if the question is, does this converge or diverge, this one converges, its value is 1. If the question is about this, I would say this just diverges. Okay, now getting a little different here. I don't have a limit of infinity for this integral, but as this lower limit goes towards 0, this approaches infinity. The graph let me sketch a little graph for you here. The graph of this is going to look like that. And so this is how the improper integral works out for this. The area I'm trying to find is this area, and the height over here is approaching infinity. So I'm going to do this the same way I normally do. I'm going to say, okay, well, I need to do the integral from 0 to 1 of, this is x to the negative 1/3. But as I do this, I'm always going to keep in mind I'm not actually putting in 0. I can't put in 0 here because it would make this undefined. I'm actually just approaching 0 from the right. The antiderivative of x to the negative 1/3, I add 1 to the negative 1/3, and I get x to the 2/3. And I divide by 2/3. And again, I'm not actually putting in a 0, I'm just approaching 0. Dividing by 2/3 is the same as multiplying by 3/2, so I have 3x to the 2/3 over 2. And when I put in 1, because I can put in 1, I get 3/2. As I approach 0, this approaches 3 times 0 divided by 2. It approaches 0, and my answer is just 3/2. So even though I have this sort of infinite height here, I still ended up getting a finite area. And again, if I were asked, I would say that this integral converges. Final example, what is this integral from negative infinity to infinity of 1 over 1 plus r squared? So I actually still need to consider this from both sides. The issue is if I try to go out to both sides at the same time, so let me show a little thing that could happen. Okay, so if I try to go out to both sides at the same time, this one, it's going to look like this. Let me just sort of graph this function. There is a chance that if I were positive and negative at times, and I try to go both ways, which this does, I could have things cancel out and get a mistaken idea that this would converge. I need to take both separately because I need this left side to converge and this right side to converge in order for this to have an area. It doesn't matter if some stuff cancels out from the far left and far right, I need them both to converge. So I'm going to first of all rewrite this as the integral from negative infinity to 0 of 1 over 1 plus r squared dr plus the integral from 0 to infinity of 1 over 1 plus r squared dr. And again, I'm not going to put in negative infinity, I'm not going to put in positive infinity, I'm going to consider as r approaches negative infinity and as r approaches positive infinity. And so in here, I know the antiderivative of 1 over 1 plus r squared is arctangent. So arctangent of r evaluated from a number approaching negative infinity to 0 plus the arctangent of r evaluated from a number, 0 to a number approaching positive infinity. Now, the arc whose tangent is 0 is 0. The arc whose tangent is negative infinity or approaches negative infinity, well, this is actually going to be, let me think about this for a second, this will be negative pi over 2. Okay, you might say, wait, hold on, why? So I know that tangent, so let me just put a little squiggle here. I know that tangent, so this is tangent, it goes through 0, 0 and looks like this. And then it has a nice little asymptote, vertical asymptote here, vertical asymptote here, and then I get another little sort of squiggle. Slopes of 1 and then going up to the asymptotes. In this example, okay, let me just do that. If I'm looking at tangent, I can see that over here, as y goes to infinity, this is getting closer and closer to pi over 2. And same thing here, as y goes to negative infinity, this gets closer and closer to negative pi over 2. What that causes for us is when I'm looking at arctangent, it's just a reflection over the identity line. And so instead of having vertical asymptotes, I have horizontal asymptotes. Instead of those asymptotes being at x equals negative pi over 2 and x equals positive pi over 2, they are now the horizontal asymptotes of, let me write this down, y equals negative pi over 2 and y equals positive pi over 2. So now you can see, as we go infinitely far left, I know this is approaching negative pi over 2 because I know what tangent looks like. I know where these asymptotes are. And the same thing happens over here. So as r approaches positive infinity, the arctangent of r approaches pi over 2. And the arctangent of 0 is 0. And so what I get is pi over 2 plus pi over 2, which is 2 pi over 2, or pi. And again, I could say that this converges because I got to a finite number. Feel free to comment below with any questions. I hope this has helped you out. And the next video I'm going to get up talks more about how I know that these improper integrals converge or diverge, some rules that are going to help that out.